our previous session of these notes, we covered the first objective, which is to recognize and describe projectile motion. And we started in on the second objective, which was resolving vectors into components and applying kinematics equations to problems with projectile motion. We just only got through the first type of projectile motion questions, which is projectile motion with an initial horizontal velocity, but where your trajectory is, you're starting on the horizontal. There's no angle involved. What we're going to talk about today is the second type of projectile motion problems where the projectile initially begins launched at an angle instead of directly horizontal. Okay? When projectiles are launched at an angle, there is not only a horizontal component to their initial velocity, but now there's also a vertical component to their initial velocity. So it complicates things a little bit because we don't only have a horizontal velocity. For falling projectiles, the vertical component was 0. We just did an example problem of that as our bell ringer. Okay? But to resolve these vectors into their horizontal and vertical components, you're going to need to use sine and cosine. So similarly as in the other problems we worked, you're going to be using sine and cosine to find horizontal and vertical components of the velocity vector, because now there will be both. One of them will not be 0. Okay? So we're just going to use sine and cosine, basic trigonometry stuff that we've been doing, applying it to a new situation. Okay? Our velocity x initial is going to be equal to whatever our velocity initial is times cosine of the angle. And our initial y velocity will be our initial velocity times the sine of the angle. Okay. So in this case, we're treating that initial velocity as our resultant vector that we are now breaking into horizontal and vertical component vectors. So just like when we did it before, it's the same here. Okay? Except now we're going to use those values that we find in the kinematics equations. If you substitute those values for the components of velocity into the kinematics equations, then you get a whole new set of equations that you can use to solve problems with projectiles launched at an angle. So that new set of equations looks something like this. And you'll notice all of these compare back to the same kinematics equations we've been using. It's just instead of saying velocity initial, we're using velocity initial times cosine. So then we talk about the horizontal velocity only. So it's the same equations. It looks messier, but it's really the same equations, just also adding in that we have to solve for that velocity to begin with. Okay? Like I said, note the equations are not random. They are the kinematics equations from before with these values subbed in. Okay? So, let's just run an example with it. Seal Sound in Scotland is a narrow strait that lies between the mainland and the island of Seal. That strait is only about 6 meters wide, which is pretty cool. It's not a super large distance. Okay. Suppose an athlete that wants to be able to jump over the sea, they leap at an angle of 35 degrees with respective to the horizontal. What is the minimum initial speed that would allow the athlete to complete that jump? Obviously neglecting air resistance. So see if using those kinematics equations, if you can get started on this, and then we'll work it as a group. All right, this problem requires several levels of thinking, okay? Because there's a couple of variables that we're not given, right? So, for example, we are not given the value of time, right? And since we know that our initial velocity y isn't 0, we can't just solve for time, right? So we have to think about the shape, the motion, that parabolic motion, and remember how we talked about at the very top of that motion, when we are at the very top of our arc, that at that point, velocity y is equal to 0, because when an object is at the very top of its motion in terms of free fall, it stops very briefly, but it does stop, right? So the same is true at the peak of the arc of the parabola of this motion, okay? So given that information and given the other kinematics equations, here's the process we're gonna run, okay? And I'm just gonna take I think I'm gonna take a blank screen and we'll come back to that one as we need it, just so I have enough room to write, okay? So we're going to remember that velocity x is equal to our velocity initial times the cosine of theta. Wow, terrible theta. Try again. There we go. Which we know is also equal to change in x over change in time. Okay? Now, at the midpoint of that jump, we know that the component for velocity y is equal to 0, and that the time required for that to happen is going to be actually half of the time necessary, right? Because the center of the parabola is at halfway of the motion. So we can write the equation, velocity of y is equal to velocity initial sine of theta plus acceleration of y times half of the time, which we know also equals 0. Because at the top of this arc, we know that the velocity of y is going to be equal to 0. So then we can do some rearranging of this equation to come up with the equation velocity initial is the sine of theta is equal to negative acceleration of y times the change in time divided by 2. Okay, we're partway there now. Now I'm just gonna kind of clear things off a little bit because we're going to substitute some stuff in. So remember that we don't have time, so we needed to solve this initial equation up here for time so that we can substitute that in for time in this equation here. Okay, so if we manipulate this equation up here to be for time, then we would have essentially just delta x over velocity initial cosine of theta. Okay, so if we take that and sub it in for time in this equation here, what we wind up with is velocity initial sine of theta equal to negative acceleration of y divided by 2 times our time here, velocity initial cosine of theta. Okay, but you'll notice that our velocity initial, we have one here and one here. We want to isolate velocity initial because that's what we're trying to solve for. So by moving things around, we'll wind up with velocity initial squared equaling negative acceleration of y times the change in x over 2 sine of theta cosine of theta. And then, of course, if we want to make it just velocity initial, we then have to square root this side. Okay? And then we can simply substitute all our values in to solve for velocity initial. So, if we do that, it'll look something like velocity initial is going to be equal to the square root of negative 9.81 meters per second squared times 6.0 meters divided by 2 times the sine of 35 times the cosine of 35. And if you run the math out on that, you should wind up with something approximately 7.9 meters per second as the minimum velocity required to do this. Of course, anything over that would also accomplish the same task. Now, I understand this is a long problem and that it requires a lot of thought. And I also recognize that it is Monday at the end of the school day. Okay, so we're going to try some other problems, but I don't want, just because the problems are challenging and difficult today, for you to feel like you will never be able to do them, because you will. Some things about science and about physics that are important to remember is that it is using different muscles in your brain than you have ever had to use before. And it's going to be a level of critical thinking that's going to be a challenge. Even if you're capable of doing the math, doing the critical thinking to get you to the equations you need for the math is going to be a challenge. It's a challenge for me, too. As I was studying this in preparation for teaching it to you, I was texting my mother going, I don't know how I'm going to teach this. I have to figure it out on my own first. And it took a bit. It's not easy. Okay? We'll walk back through these steps a little more slowly. Okay? So the first equation is just one of the kinematics equations where we have velocity of x is equal to velocity initial times the cosine of theta. And then we know that velocity x is also equal to a change in x over a change in time, right? Because that's just our basic. Okay, so the last set of equations that we did from the previous slide, okay, and also the fact that we know from basic science velocity is equal to distance divided by time, right? So if we're solving for the x component of velocity, the x distance, or change in x divided by time, should give us that velocity. And we also know that if we're solving for the x velocity having been given an initial velocity that's in several different directions, that we can solve for the x component of it using the cosine of theta times that initial velocity. So what we're saying is both this piece right here and this piece right here are equivalent to velocity x and therefore equivalent to each other.
So if we were trying to solve for velocity of y, would it just be change of y over time?
Yes. Yep, if we were trying to solve for velocity y this way, we could say velocity initial times the sine of theta is equal to change in y over change in time. The same equation applies. Yep. Okay, we're going to back up quite a ways. So that's our first equation. That's where we got it from. Pieces from our understanding of basic physics and pieces from our understanding of resolving vectors into their component vectors. And we're just combining them here. Okay, then the next equation is slightly trickier. Okay, because what we're doing is taking our velocity y equation, and we're saying, just like we did before, that velocity initial is equal to sine of theta. Okay, that would give us velocity y, just based on the idea of resolving a vector into its components, right? And we also know that velocity y, from the kinematics equations that we've been using, right, velocity y is equal to acceleration of y times time. Okay? You can do that. Sorry, those two are equal. However, we had to change this equation slightly because we want to be able to move things around a little bit. So what we also want to be able to say is that this is equal to 0. But we can't say that as is. We can only say that if the time value is equal to half of time, because that's when we reach that top of our arc on the parabola where velocity y does in fact equal 0. So we want all of these things to also be able to equal out to 0, and in order to do that, we have to take the value of time from our equation and divide it by 2. To say when time is half, when we are at the half time point, then this is also equal to 0. which allows us then to manipulate this equation and be able to solve for some of the variables that we don't have, so that we can sub things in and have values. Because we have too many missing values to run it standard, right? We would need a time to make this a less complicated problem. So now we're going to try and take this equation right here and sub in an equation for time into it, so that then we can have one less variable. And that's where we came up here, and we said, hey, remember from this equation, we could solve this equation up here for time. And if we did that, then we would, if we solved it and moved it around so that time was by itself, the rest of the equation would be delta x over velocity initial cosine of theta. Because what we're doing is we would multiply, this side by time, and then we'd divide by velocity initial and move it over here, and we'd wind up with this equation that's down at the bottom. So now we have a delta t to sub into the equation up above. So if we do that, and I'm just going to erase some of these things so I don't have to clear the whole screen off. If we sub that equation in for this t spot right here, in for the t spot that's here, we wind up with velocity initial sine of theta equal to acceleration. Oh, I suppose we also have to move some stuff around so that there's not too many parentheses things going on. Let's back this up. We want to move acceleration of y up to the top of this. So in order to do that, we are simply going to make it negative.
Why is making it negative when you go to the top?
It's part of that, I believe it's part of the multiplying by the reciprocal thing, but I would have to actually clear that with your math teacher because that's a part that I don't fully understand. So you move that up there and you wind up with velocity initial, goodness, not what I wanted to do, sine of theta equal to negative acceleration of y over 2. And then take that times time. Okay, so it's the process of getting this time out of the fraction and by itself so that we can multiply that makes that acceleration negative. Then we can sub in for time here. So we have velocity initial sine of theta negative acceleration of y over 2 times our time, which we are subbing in the previous equation for. Okay. And then, so if we divide this side by velocity initial, or not divide, sorry, multiply, because it's on the bottom of that fraction. We multiply this side by velocity initial, then we also have to multiply this side by velocity initial, which is where we get the velocity initial squared, and then we have to divide this side by the sine of theta, so we also have to divide this side by the sine of theta, so velocity initial disappears from over here, and sine of theta disappears from over here, and we are left with velocity initial squared equals negative a y delta x over 2 sine of theta cosine of theta, and then we just square root to get rid of that. Does that clarify a little bit more?
Yeah, just the other thing I guess I was a little confused with was the velocity y, like in getting that acceleration y time, the time thing, like doesn't that come from the, like I didn't know where that came from.
The velocity y equals acceleration of y times time. That's just one of our kinematics equations. So if you go to the previous page, you can see that.
Which one? Is that the third one?
Mm-hmm. I believe so.
And how is sine so much? I never mind.
Because we divided by
I
it.
just don't understand how it's negative. Like, that doesn't make sense. Because if you do the reciprocal, then it'll just...
So what we're trying to do is take ay, right, which we're essentially saying is ay over 1, right, and we're taking it times t over 2, and we want to get the t by itself and out of this fraction, right? So, you know, I would say probably just ask Mrs. Siki, because this is a piece of math that is not making sense to me personally. Like, I am following their instructions to say that it becomes negative there, and now you have that equation to use for the future, so it's not like you're going to have to do it for yourself. But I could not tell you why that piece there becomes. I could go look it up and try to figure it out, but I could not. It's algebra, some kind of algebra that they use to get this by itself caused that. All right, here's our problem, is my brain was being dumb and thinking of the wrong equation. They're not just saying that Vy equals the initial sine of theta, which also equals this. That's not what they're saying. They picked a totally different equation, and I missed it. They picked the kinematics equation where you have velocity of y is equal to velocity initial plus acceleration times time. That plus sign there is where the negative comes from, because when we solve it like this, right, so we have velocity initial sine of theta plus acceleration of y times half of time, okay, equals 0. So we can essentially, by saying equals 0, get rid of this piece, okay? So now we're moving this to the other side, but in order to do that, it's not a division problem, it's a subtraction problem, okay? So if we're moving this bit, or rather it would look like they moved this bit to the other side, that's why it's negative. It's a subtraction problem. So now we have velocity sine of theta, and they subtracted it, so it's equal to negative acceleration of y, change in time over 2. And then they just combined the equation.
That's why I was confused.
Yay, we figured it out!
Dy, because I was like, there's only half of the equation. Because when you said Vy equals...
You're right. If we had been using the equation I thought we were using, we would be missing part of the equation. So we were using a different equation than I recognized. So, but we figured it out. Good. Okay.
Someone has that all written down. So.
A deep breath in. Okay, it's all available on here, which I'm gonna put online, even though we have this whole discussion in the middle where we have to figure it out. But hey, that's part of physics. We're all learning together this year. Okay?
You just gotta know that it equals something like that.
Yep. So, do we feel a little more comfortable with manipulating the equation?
I get where each part came from.
Right. Doesn't necessarily mean you can do it by yourself tomorrow, but you get where the pieces come from.
Yeah.
Okay. Your homework is 1 through 3 at the end of this section. And that's kind of what we'll start with tomorrow, is going over those problems. So please have attempted them. Okay? The page is 101.